From the previous lesson, you have learned that the Newton's law of gravitation, which states that if there are 2 point masses which has the mass m1 and m2, the forces of attraction between them is gmm over r squared, where r is the distance between them. Until now, all the examples that we have seen so far involves 2 stationary mass. So from now on, let's explore the case when a mass is orbiting about another one. Take for example, let's imagine this to be the Earth and this to be the Moon, and the Moon rotates around the Earth with a fixed radius. We can also see the rotation from the top view. Let's analyze it with a simulation. In this simulation, you can see that the Earth is at the center while the Moon is situated at the top. From the previous lesson, we have learned that the forces of attraction between them is equal in magnitude but opposite in direction. Let's set the Moon to rotate about the Earth in the same way as before. We can see that the forces of attraction between the Moon and the Earth is always the same at any point of the orbit. Now let's try to draw the free body diagram for the Moon. When drawing the free body diagram, we assume that there are no other masses near the Moon. Thus, the only force that acts on the Moon is the forces of attraction due to the Earth. And this force is given by gmm over r squared, where r is from the center of the Earth to the center of the Moon. Do note that as the Moon is rotating, the force is always the same at any point of the orbit as shown by the simulation. So, we have been talking about circular orbits whereby one mass revolves around the other. This must be very familiar to you as we have just covered circular motion a few weeks ago. In the chapter, we say that if a mass is orbiting round in a circular orbit, it will experience a centripetal force which is pointed towards the center of the path. So now let's link the motion of the Moon when it's orbiting around the Earth with circular motion. From the chapter, we know that the centripetal force is equals to mv squared over r. If you can't recall anything from that chapter, it would be good to take out your lecture notes now. Note that the Moon is rotating with a fixed radius about the center of the Earth. Thus, the force during the rotation is always the same as the force is determined by gmm over r squared. And we then equate the force with the centripetal force. And by simple mathematical manipulation of making v the subject, we will realize that the velocity of the Moon while it's rotating about the Earth is square root gm over r, where m is the mass of the Earth. Note that for this example, we say that the m1 is a Moon. However, it can be satellite or any other body that rotates about the Earth. Okay, so that is for the velocity. How about the other properties when it is orbiting about the Earth? Let's say the energy. You have learned that when there is a large mass, m, and that with a small mass orbiting around it, its gravitational potential energy will be minus gmm over r. And furthermore, this is constant throughout the orbit as r is a constant. Then how about the kinetic energy? This can be derived by equating gmm over r squared with mv squared over r. As kinetic energy is half mv squared, so we make half mv squared the subject and we get that the kinetic energy is gmm over 2r. Thus, if the potential energy is minus gmm over r and the kinetic energy is gmm over 2r, the total energy is simply the addition of the two. So, minus gmm over r plus gmm over 2r, it gives you minus gmm over 2r. And that's the total energy. Confused by all the formulas so far? Not to worry. All of them are derived from gmm over r squared minus gmm over r and mv squared over r, which all of you have learned before. If you don't believe me, we can review at this formula. The gravitational potential energy is simply minus gmm over r. The kinetic energy is derived from gmm over r squared and mv squared over r. This is the same for the velocity of the mass. We have come to the end of this video, and let's do a recap of what we have learned so far. We have talked about orbiting mass and their properties. And we have learned a lot of new formulae. No, actually, these formulae that we described are just derivable from the three equations. Finally, you are to carry on with this TechEd lesson, and we will talk about geostationary satellite to give you a real-life example and appreciate what you have learned so far. See you next week in the next lesson.